Uh, Welcome to second problem solving session for the course Fundamental of Semiconductor Devices, NOC 24E82. This is hosted by NPTEL. This is the second week that we are meeting on February 3rd, 2024. My name is Amit. I am a PhD student at ISC Bangalore. Just quick recap what we had talked about in the last session, where we saw the classification of materials, primarily metals, insulators, and semiconductors, and we saw that where we classified them based on their electrical conductivity. Just a second. Classified them based on their, this doesn't seem to be working, based on their electrical conductivity. Okay, so electrical conductivity was what we were concerned about. And then we also saw the band gap. So we saw that there is, let's say this is the conduction band, this is your valence band, right? And then we could see that there is a gap in between, right? What we refer to as EG, right? This is what we had called it. And yeah, so this is the band gap that we were talking. Just give me a second, I'm having some technical problems. Sorry about this. I'll resume the session, just hold on. um, okay, let me try to restart. Okay, so we had I've seen the classification of materials where we're talking about in terms of electrical conductivity, and we saw one of the key reasons that semiconductors are so good is that as someone pointed out, that their conductivity is tunable, right? Secondly, we saw the origin of a band gap in a semiconductor. So let's say this is the conduction band EC, this is EV. So the electrons can reside here as well as the electrons can reside here, but this is forbidden. In this range, electrons cannot reside, and this is also known as band gap, energy band gap, or forbidden energy gap. And we also saw that if we, like for instance in LEDs, right, if an electron is here and if it comes here, we saw that it can emit a photon of energy exactly equal to Eg. Finally, we saw something called the effective mass, which is very very critical, because please understand that fundamentally that everything is happening in a lattice. We regularly take the example of a silicon lattice, and we saw that that Ronick Penny model, we saw that they have a periodic potential of something like this. It's periodic potential in which electron is traveling. And in this we can saw that we also saw the EK diagram, right? EK diagram, or also called the band structure. We saw that we saw it looks something like this. For instance, let's say gallium arsenide, which is a direct band gap semiconductor. So this is your conduction band, this is your valence band, and we saw there is a curvature over here. This is E versus K. This, the diagram over here, is E versus, let's say, X, real space. K is your reciprocal space, 2 pi by lambda. Lambda is the wavelength. Finally, we saw something called the Fermi function. I'll again touch upon the Fermi functions, so I'll leave it at that. So in the last class, a question was put up as to what a Fermi Dirac Statistics is all about. What is it? What do we understand? So for instance, because as we also saw that in the last session, there are significant number of people are from first and second year of their bachelors. So let me try to break it down so that they are able to comprehend what is happening. Essentially, this statistics we are talking about is just we are talking about distribution. So please understand that when we talk here, we are not talking about a single electron or a single entity. There are millions, billions, and not even that. There are 10 to the power 12, 14, or 19 and such entities. such electrons, maybe 10 to the power 23 even, in a given volume, right? So there we cannot precisely pinpoint where it exactly lies, but of their whole collection of, let's say, 10 to the power 23 electrons, 10 to the power 23 electrons if there are in total, we can say that okay, 10% of them are in this much energy, have this much energy, 1% of them have this much energy. So that's what is a probability distribution is talked about. What are fermions? A good example of fermion is electron, but a formal definition is that fermions are so in particle physics there's a whole branch of elementary particles called fermions. Here I am just putting the very simplistic definition which you'll be able to understand. Fermions have half integral spin. By that I mean 1 by 2, 3 by 2, 5 by 2, and so on. Half integral. So it's like that, not an integer. They follow Pauli's exclusion principle. This you have read about in high school physics or chemistry, that when two electrons come close together, they cannot, if they're all the quantum numbers are same, they cannot reside in the same state. That's why they have a up spin and down spin, right? But that spin is also a spin quantum number. Essentially, fermions are such entities, and there are other more specifications to them. For instance, these fermions, all the fermions are identical. So for the electrons in the system, when you talk about 10 to the power 23 electrons, they are identical. You cannot say okay, this is electron 1 and this is electron number 10,000. No, you cannot pinpoint them. They are identical in every sense of the word. They have different quantum numbers, but otherwise you cannot distinguish them. They are indistinguishable. Okay, and what we want to do essentially, when I told about that a huge number of electrons and we want to arrange them, so how do we want to arrange? And Professor Digbijay explained it in his lectures. I'm just going to borrow it from this. So let's say this is some energy state E1, okay, any energy state E1, and let's say you have G1 states that are available here, G1 states, and what I want to do is I want to fill n1 number of electrons here. So I repeat, this is same energy level E1, and there are different energy state at the same energy level E1. There are G1 occupancies, there are G1 vacancies, and there are n1 electrons that can come and reside over here. Similarly, there is another energy state E2 which is higher than E1, and again here there are different vacancies, G2 such vacancies, and here I want to fit n2 number of electrons, and this continues. So ultimately, let's say the final energy state is En. Again there are Gn such vacancies here, and the number of electrons that I want to put here is Nn. Okay, so this is if I want to arrange such a system, right? I want to see, so you can do the combinations here, right? Your permutations and combinations over here. So if you go ahead arranging them, right, you are interested in finding the probability. So for instance, you're finding the probability that I want to know whether, let's say, for any random energy state, which I'll denote in a different color for sake of understanding, what I'm interested in finding is that in some any energy state EI, which again will naturally have GI buckets, how many number of electrons Ni are residing there. So that is my problem statement. So I'll just repeat the problem statement. The probability that Ni electrons are in EI energy level. If you look at it, since this is I told you these are indistinguishable identical particles, you will simply say Ni over Gi, very simply, because there are n particles to be distributed and there are Gi spaces that are available in this energy level. I am interested only in this energy level, so please understand this is in the blue color that I am writing. However, there is a formal way of doing it. As I told you, if you go ahead and try at finding the permutations, again I'll request you to go to the last video of first week by Professor Digbijay Nath. You just, in this course, you just go to that, and where he calculates the combination. So for instance, it will be N1CG1. Corresponding to this, it will be N2CG2, and then we multiply all of them. So we multiply to find the probability. We run from I equal to 1 to capital N. It will be NiCGi, right? So essentially what happens is that this probability that I have written here very simplistically, it is related to this. Okay, because you see the term I that is coming here, this is closely related to this. So what happens is that when you do this mathematics, you're not going to do in this course or in this session for that matter, you just have to trust that when you do this analysis, this is how the function's final form comes out to be. This is how the final form looks like. This is again the same. So I told you the probability that we are interested in finding this. So let me say it formally, that FEI, which was equal to Ni over Gi, this is same as this entity. Okay, but for any given value, for any given energy Ei, what is the probability that it is occupied? This is the same problem that we talked about here. You see in this, so here the energy is increasing in this direction. Increasing energy. The GIs are what we typically refer to as degeneracies. Degeneracy is just a fancy word of saying that they have the same energy. They have slightly different characteristics, because please understand that they still have, because we are talking about the distribution of fermions here, they still have to follow the Pauli's exclusion principle. Okay, so this is the formal way of doing it. You see this capital pi, where we multiply all the possible combinations and then we minimize this function, right? But essentially what we are interested in finding this number, right? So when you find this number after doing some mathematics, what you find is that this is the result that comes out to be. This is the exponential function that comes out. How is it defined? It defines is that, so here what we have invoked is that we have gotten this entity, something called EF. We also call this Fermi level. This is purely a statistical entity. Okay, this is purely a statistical entity. How does it come about? When you minimize the function, the multiplication that we saw of the combinations, when you minimize that, you get this form. And what is it formally defined? Formally it is defined the same definition that we seen earlier. Probability of finding an electron at any given energy level E. So here I have dropped the I here. E is the variable. So this was the same definition as this. Please recall.
If temperature goes to 400 Kelvin, then middle point would be 0 Kelvin, or it would be different.
Can you please repeat? If the temperature goes to 400 Kelvin,
then middle line Fermi level, which is at T equal to 0 Kelvin. So
Yes.
would it different, or it would remain same at T equal to 0
it would
Kelvin?
remain the same. See, that's what I'm saying. Fermi level, this is just an arbitrary level that I'm defining. That's what is this definition? So its definition is that Fermi level is that energy level. Fermi level is that energy level at which, below which, all levels are filled at 0 Kelvin. This is the complete definition of a Fermi level. Fermi level is that energy level below which all levels are filled. So first of all, I need to consider only a T equal to 0K. So if you see at any energy level, I'll denote it with the green color. So let's say I talk about this energy level E1. Sorry about this. Give me a second. Okay, let's talk about this energy level E1. So this energy level is below EF, fine, and let's try to find its probability. So how to find the probability? Just go in this direction, keep on going, and it's hitting over here, this point. What is the value on the x-axis? It's 1. So this means from at this point. So this satisfies the definition. Below EF, all the energy levels are filled. That's why you see this vertical line over here at T equal to 0 Kelvin. The situation changes for different temperatures. So for instance, in this curve, a blue line has been drawn, which corresponds to T equal to 300 Kelvin. Okay, how does the picture change? So again, two things do not change. What is that? That below Fermi level, so exactly at Fermi level, the probability of finding is half. That's why I told you in the last session, I also talked about this. There are different ways of defining the Fermi level. So Fermi level, this is one definition. Fermi level is the level, energy level, below which all levels are filled at 0 Kelvin. This is another definition. Shall I write? This is the first definition. The second definition is level at which probability of occupancy is equal to 0.5 at all temperatures. You see T equal to 300 Kelvin. At this energy level E equal to EF, the probability is still half. I'll show in blue color what I mean. So blue color corresponds to T equal to 300 Kelvin. Look at this point. This point is lying on this this curve at E equal to EF. The probability of finding electron is exactly half for T equal to 300 Kelvin. Let's draw one more line of 400 Kelvin, which I am going to draw in purple. Okay, so let's draw that in purple. It will look something like this. This purple curve is T equal to 400 Kelvin. Again you see the same point. This definition is again satisfied. Probability of occupancy equal to 0.5. So at T equal to 400 Kelvin, that is the purple curve. If you see E equal to EF, again there the probability of finding is 0.5. There are two more things as I told you. Above E equal to EF, the probability of finding is always less than 0.5 for every temperature. So above E equal to EF, so let's say I talk about this temperature, E2. At E2, I'm interested in T equal to 400 Kelvin. So let's say I'm over here. What is the probability? Probability is less than 0.5, maybe even 0.1 or 0.2. We don't know, but it's less than 0.5. Let's say another temperature, another energy, sorry. Let's say E3 over here. Again, interested only in purple curve. What is the probability? Probability someone over here. So below EF, the probability of finding an electron in that particular energy level is always greater than 0.5. You see it's somewhere over here, maybe 0.9. Right? And this, and above EF, the probability of finding electron is always less than 0.5. Let's say this was 0.1. So let's illustrate it. So you can draw as many temperatures on this as you can. These things do not change, because please understand, EF is a statistical construct. It's statistically we are defining it as such. Alright, so here in this chart I have shown three temperatures: 0 Kelvin, 300 Kelvin and 400 Kelvin. The three key things that here are: at E equal to EF, energy of occupancy is always 0.5 irrespective of the temperature. Okay, below above energy level EF, the probability of occupancy, that an electron is present at an energy level above EF, is always less than 0.5. This means I am in this region, which you can see I'm above EF and probability is less than 0.5. At all energy levels below EF, the probability of occupancy or probability of finding an electron in that energy level is always greater than 0.5, which is this region where my cursor is. Alright, this is the takeaway from this. So we started Fermi Dirac Statistics, which is applicable to fermions. There is a whole mathematics that is involved. Effectively, it just condenses down to this. And honestly, this is the thing that we are interested in. We do not care about how we reach there, but we know this is a well-behaved formula. There are some assumptions here that is true, but for the most part, this holds true. This is a very simplistic formula dependent only on EF and on temperature. And here I have depicted the role of temperature. Alright. I hope that answers your question. I'll still wait if you have any doubts or questions here, because this is important. This keeps on coming over and over again. Fermi function, not just here, but in some part of it is always, if for the people who have physics background in thermodynamics, this concept comes over there even. Okay, if we are good, we had talked about in this last class also, but I just felt important to revise it again. Okay, so now we know that what is the probability of finding an electron at any energy level E, right? But next question is, how many such energy levels are there? That is defined, that is determined by an entity called density of states. Okay, so what I'm talking about here, so I'm talking about this here. So we now you are habitual of seeing this EC and EV, right? And there is a band gap that you can see over here in the middle of them, right? What I've shown here is that, taken from this source from University of Berkeley handbook that I found. So I'm taking any infinitesimal energy levels, energy chunk delta E, right? So what I'm defining a density of states is the number of states that are there. So what I'm doing here is essentially, please, I told you this is a band, right? That's what we have been told, this is a band. What I'm assuming that this is not a continuous band, but rather at discrete levels spaced very close to each other, which is actually true. Quantum mechanically, we had talked about in the last session also, they are discrete levels, right? So I'm taking that for any, this is the variable that I have, delta E, right? So how many sub number of energy states, 1 2 500 5 million, how many are there, divided by delta E into volume. So why volume? See, this is happening at, this is actually a E versus X diagram, energy versus space, right? I have drawn it one dimension, but it can be drawn in three dimensions, so because the materials that we encounter are typically three dimensions, hence this term volume. So what will be the units? This is number of states, this is unitless. Delta E, it's the units of energy, which let's say electron volts. So electron volts inverse. Volume typically is your meter cube, but here we prefer CGS. So here we go centimeter minus 3. So this will be the units for density of states. Again repeat, what is the density of states? Density of states is you take any infinitesimal small number of energy here, that is denoted by delta E here. How many states are there? 1 2 5 10, right? Then the numerator divided by the spacing that you have chosen, right? This is just like integration and differentiation where you choose dx, right? Same thing here, so delta E or dE times volume, because we normalize with respect to the volume. It's fine. So very simplistic question will rise, how many energy states, what will the density of state in this region? It will be 0. Please remember, this is a forbidden energy gap. Forbidden, this space is forbidden. How many energy states will be there? 0. So dc in this region is 0 in this region. There's no density of states over here. Why? Because there is no state. There's no state that an electron can reside in. Alright? Please always keep that in mind. Usually when we talk about density of states, you always see in terms of EC and EV, right? Where we talk about conduction band density of states, valence band density of states. What's happening in the middle? Nothing is happening because it's forbidden. So density of states is 0 over here. Alright. So now we have seen that we discretize in the conduction band. The same story actually goes for valence band also. It's the same thing. Okay. Now how do we define that? So the thing is, it's more there's a rigorous algebra involved, which we do not go into this course. But just so happens that for three-dimensional systems, the density of states comes out to be directly proportional to density of states comes out to be directly proportional to square root of energy. Directly proportional to square root of energy. This is some constants that come into picture. So please, one thing you can clearly see, when we talk about conduction band density of states, we are considered about electrons. This N stands for negative charge, which in this case is electrons. For valence band, this is conduction band. This is valence band. For valence band, we are concerned about the holes. What is a hole? Hole is nothing but the absence of an electron. So for whatever reason, if an electrons were here, it went to conduction band, there's a vacancy that is left behind. We call that a hole, denoted usually by P. So you see, when we talk about valence band, we talk about holes. So density of states for holes, for conduction band it is electrons. As I told you, why E only greater than EC? Because below EC, first of all, there's a forbidden energy gap, so we can't talk about here. Hence this term E minus EC, I told you, is directly proportional to E. Starting point itself is EC, hence it looks like this. If you want to express it in terms of your graphically, it's a quadratic dependence, right? So that's how it's been determined here. So you see this parabola, this is the quadratic dependence. All right, so that's how we are depicting them over here. And similarly goes for valence band. Usually I'll be talking more exclusively on the conduction band, but the same story goes for valence band as well. All right, so the key takeaway from this is that the definition of density of states. So please recall, in Fermi, when we talk about Fermi function, we talk about what is the probability that an electron is in a given energy state. Here I am saying that where is that energy state. Okay, so when you multiply those two figures to arrive at the carrier concentration, that means there are two carriers, as I talked about, electrons, the negatively charged carriers in the conduction band, and holes, the positively charged carriers in the valence band. Okay, how do you determine their concentration? Simply you integrate it from, remember this diagram over here. How do you calculate the concentration? It's simple. The energy states, the density of states that you have, right? The density of states you have times the probability that their energy state is occupied, and you integrate them. Remember this TE. So what you get is centimeter minus 3. Remember, this is unitless. This is just the probability. What were the units here? EV inverse centimeter minus 3. DE is nothing but your infinitesimal, this chunk here, or if I define it, this is the DE I'm talking about, this thing. Okay, this is what energy units. What is the total units? Centimeter minus 3. Hence the concentrations that we typically report are they have the units centimeter minus 3. Okay, and we're integrating from EC to top of conduction band. Where is the top of conduction band? Infinity, in fact. You integrate this function, you know Fe, which is the exponential form 1 upon 1 plus exponential E minus EF over KT. DC expression we saw in the last slide. D is just the variable that we have, and you integrate that. These are the values that we saw in the last slide, that in density of states for conduction band has this expression. N stands for electron, and this is the parabolic form of E minus EC. Fe we saw in the Fermi function in the last session also. Graphically, this is how it's depicted. So again, black is your electron, solid circle is your electron, hollow circle is your hole, which is shown over here, right? So this is some arbitrary energy level EF over there. How does the density of states look like? As you saw, it looks like a parabola, like this for conduction band, similarly for valence band. What is the probability? We have already seen that at E equal to EF, the probability will be exactly half, which you can see over here. Below EF, the occupancy probability will be more than half. You see, that's why this value is more than half. Above EF, the occupancy probability will be less than half, which is, you see, in this part of the region, this part of the plot, sorry. What is the carrier distribution? As I told, this is simply the multiplication of Fe times the density of states, and then we integrate it. That's what we'll integrate this portion actually. Here, this is just the multiplication. That's why it's called carrier distribution. If I want to define it, it will be Fe times dE. E is any given energy. That's why you see on the y-axis. How will it look like? So see, in this region there is no density of states. That's why electrons, you don't see any concentration of electrons over here. In this region only you can find electrons, which is clear because DC of E exists only above EC. But you see the probability goes on decreasing, right? Hence you see this tapering off. Simply you multiply this. So earlier the graph will tend to, this will have this shape, and then it will peak at some point, it will gradually decrease. Similarly the shape for holes, right? This tailing off happens because you have very less probability at higher and higher energies. There's very less probability that higher energy electrons will reside at higher energies, even though there are more states. Density of states is essentially the number of states that are there, right? Even though there are more states available, but their probability of occupancy is so low, the electrons will not be found. Electrons will be found very close to the conduction band, and holes will be found very close to the valence band. So this is one again. This again, knowledge that you gain just by multiplying density of states times the probability of occupancy or the Fermi function. All right. When you do that, so when you put these two expressions over here, you integrate that, what you get is this kind of a form. This is simply just this is arrived. This expression is arrived just by integrating this. Okay. So this is again in centimeter minus cube. This is the concentration of electrons in the conduction band, and naturally it depends on EF, because the way EF shifts, you can see the curve will shift. It can shift up and down, right? And what you see, this NC term over here, this is also known as effective density of states for electrons, mind you. I have not written what comes for holes, but it is denoted by NV. Here it comes in place of N, there is a P, and the formula is minus of EF minus EV. So it's very symmetric. We'll solve when you solve a couple of problems, then we'll get to know that. All right. So this is the complete picture. So first, so in order to arrive at how many electrons or holes are there, we first need to see what are the different energy levels, what is the distribution. That is given by the density of states, which you see over here, and then you multiply them by the probability that particular state is occupied, which is given by occupancy probability. Finally you get what is the carrier distribution, and then when you integrate it with respect to the differential energy component, you get the total number of electrons that are there. And again, as I told you, you can see that the number of electrons that are being occupied at higher energies will they in fact drop very close to exponential, because remember, this is an exponential function, this is a quadratic function. At higher values, the exponential will clearly dominate the quadratic function. Similarly goes for holes. So essentially most of the action, so to speak, is happening near the band gap. So most of the electrons are residing just above the conduction band. Most of the holes are just below the valence band. That is the takeaway I want you to have from this discussion. Okay. So I'll again wait for some time, and I'll pause here if you have any comments or questions, because now we'll just go ahead and solve the problems. But I specifically wanted to spend some time on this, just so that it becomes very clear that where the electrons come from, how are they related to the probability of occupancy or the density of states. So this slide contains all that information. All right. Okay. So if there are no doubts, feel free to stop me anytime. Like sometimes I can go fast.
If Fermi energy level 0.2 electron volt below conduction band,
Yes.
occupancy of finding electron or probability is zero or is something else in this graph.
Okay, so let's let me just make sure that I understood your question correctly. So saying if EF is below, let's say 0.2 electron volts below the conduction band, right? What is the probability of occupancy of an electron at EF? That's your question?
Yes, sir, sure.
Yeah, so it will still be half. See, again, please understand that occupancy probability doesn't care about density of states. It simply cares about what is the Fermi level and what is the temperature. That's it. Density of states and occupancy probability are two entirely independent constructs. So even though the probability of finding electron here is half, you will say, okay, then I must find some electrons. You cannot find any electrons here. Why? Because there are no states to be occupied. Occupancy probability says that if there is an energy state, this is the probability that electron will be there. But unfortunately or fortunately, there is no energy state over here. There is no energy state. You can see the density of states, it's non-existent. It's a forbidden energy gap. So even though we have a finite probability of finding the electron here, we'll never see any electrons in an ideal crystal, because there is no energy that can be occupied. Probability is there, but there is no energy. So it's like x into y. You are saying y equal to 0.5. Very good. What is the value of x? X does not exist. X is 0. It exists, its value is 0. So there is no energy state to be occupied, even though you can have a probability of occupation, right? That's why the electrons, number of electrons that you will find over at this energy level EF is going to be exactly 0. Does that answer your question? Vinod, that's what.
Yeah, sure, sir. I am. You have mentioned probability is there. So, what would be the probability means determination means in that state?
No, in that state, that will still be determined by this expression. The
Okay,
probability
okay,
probability will
okay,
still be there.
okay. Sure, sure, sir. Sure, sir. Thank you.
Yeah, all right, good. Okay, so now based on this basic understanding, now let's try to put this knowledge that we have, some preliminary knowledge of carrier concentration, to some problems. Now this will be now more into mathematics and less into physics. All right. Okay, so this first question, sorry, yeah, so first question for today, it says that the band gap of silicon depends on the temperature. Sorry, second. The band gap of silicon depends on the temperature as this expression. So till now we have been saying that the band gap is this. When I draw the Fermi function at T equal to 0 Kelvin in 300 Kelvin, I was simply saying that it stays fixed. It does not stay fixed. It depends on temperature using this expression. Fine, well and good. We do not worry much about it. Because most of the experiments or the studies that we do, right, usually happen at T equal to 300 Kelvin, and this is a weak dependence on temperature, which we'll see in this problem. It does depend, but it's a weak dependence. Okay, what we are required to find is find the concentration of electrons in the conduction band. Okay, so just to be clear, we are required to find this. N is the concentration of electrons in the conduction band. So we are essentially required to find this. Okay, of intrinsic or undoped, I'll come to doping, but anything which does not have any impurity is intrinsic, which is undoped, is known as intrinsic semiconductor. Anything which has some impurity added to it, it is called a doped semiconductor or a extrinsic semiconductor. Okay, here we are only interested in intrinsic semiconductor. Now Ni, so there are few more concepts that I did not touch upon in the last slide. So for any intrinsic semiconductor, so let me define it here. For any intrinsic semiconductor, what happens is that the number of electrons in conduction band denoted by N is exactly equal to number of holes in the valence band denoted by P, and we denoted something called an entity called Ni. We don't use Pi, we just use Ni. This is the intrinsic concentration, and it depends on temperature. So for instance, at 300 Kelvin, this value is around 10 to the power 10 centimeter minus cm minus 3 for silicon, which is written over here. I'll just drop this first term, it's around 10 to the power 10. That's the extrinsic semiconductor. Okay, this is called the electron carrier concentration. I'm just writing it again just to be very clear. This is the electron concentration naturally in the conduction band. This is the whole concentration in valence band. This is what we refer to as the intrinsic carrier concentration. Okay, three entities, different entities, but for intrinsic semiconductor they are the same. When we introduce doping, I'll again come to this concept, but we'll see then these values shift. All right, okay, now let's come back to our problem. So what we have is that we are given Ni at 300 Kelvin. Okay, how do I get Ni? I can there are different ways of arriving at that. Okay, so the simplest way, I'll do it in this way. So this is the expression for N, right? I'm just going to do the analysis first. At just write the expressions. N equal to NC exponential of EC minus EF over KT, and P will be nothing but NV, density of effective density of states for valence band, EF minus EV over KT. I'll simply multiply these two entities. Remember, this discussion is for an intrinsic semiconductor. NP will be nothing equal to Ni squared. Simply because N equal to P equal to Ni. What will I get? I'll get NCNV times exponential of, I'll write it, EF minus EV minus EC. Just let me be clear that I'm doing it correctly. EF minus EV, if I'm multiplying them, minus EC okay. So what I'm getting here is this, it's minus of EC minus EF, so here it will be EF minus EV. Yeah, that's just a second. Oh no, it will be EF minus EV. Sorry, this is EV minus EF. Okay, so it will be minus EV this. I'm just multiplying these two, so exponents will simply, the powers will get added up. So what I'll get is Ni square equal to NCNV times, okay, NP equal to Ni square, by the way, is also known as law of mass action. So this is a term that's repeated, law of mass action, and N into P is equal to Ni square. We'll use that repeatedly for in this session. NC into NV, so this comes out to be EF and EF gets cancelled, right? What you get is EV minus EC, which is nothing but minus EG over KT. So what I get here is Ni equal to square root of NCNV times exponent of minus EG over 2KT. What you see clearly over here is that intrinsic carrier concentration, first of all, depends on the effective density of states NC and NV, right? And NC and NV, you see, depend on the effective mass as well as the temperature, all right? Also, you can see that it also depends on EG. Someone Rohini, can you please mute yourself? Okay, so what you are interested in finding, the intrinsic energy level, the intrinsic concentration of electrons, which is this same Ni equal to N, because we're talking about an intrinsic semiconductor. We are interested in Ni at 77 Kelvin. This is what we are interested in finding. How do I do that? Now it's very simple. I say Ni at 77 Kelvin, I take its ratio with 300 Kelvin. This should be equal to square root of NCNV at 77 square root of NCNV at 300 exponent of minus EG over 2K into 77 exponent of minus EG over 2K into 300. I know this entity, so I can get Ni at 77 Kelvin equal to Ni at 300, I know, is around 10 to the power 10 centimeter minus 3 times. First, let's see this term, NCNV at 77 Kelvin. How will I find the value? All of the terms will get cancelled except for temperature, right? So what you will get here is simply 77 raised to the power 3 by 2 into 77 raised to the power 3 by 2 over 300 raised to the power 3 by 2, 300 raised to the power 3 by 2. Why I am repeating them twice? Once for NC, once for NV, right? Rest of the terms Mn star, H Planck's constant, all of them will get cancelled, multiplied by exponent of, now I need temperature at 77 Kelvin, sorry, band gap at 77 Kelvin. So I'll simply put the value here. So I get Eg at 77 Kelvin equal to 1.17 minus 4.73 into 10 to the power minus 4. This is 77 into 77, 77 squared, that is, over 77 plus 636. You calculate this, I think comes out to around 1.166 EV. Okay, you put that value here. So minus 1.166 over by 2 times Planck's constant. This is in EV, mind you, over into 77, divided by again exponent of, again you put Eg this time at 300 Kelvin. You put T equal to 300 in this expression, and I did that. This turns out to be around 1.125 EV, divided by 2 times K times 300. Now this is nothing, just mathematics from now on. So I solve this and it comes out to be around 10 to the power minus 20 centimeter minus cube, cm minus 3. Unit cm minus 3 comes because this Ni also cm minus 3, which was given to us in the problem itself. Okay, that's how we solve this problem. Mathematics is fine. Key thing is, what do we understand? We learned two things from this. First, the band gaps, even though we say they do not depend on temperature, usually we do not see in our problems, they do depend on temperature, which has such a dependence, T square over K plus T, something like that. Secondly, we see how the intrinsic carrier constant. So first we introduce the concept of intrinsic semiconductor, in which there is no doping. So all the number of electrons in conduction band, which makes sense because some of the electrons which are there in valence band, they just went to the conduction band, and thus the electrons which are in the conduction band has to be equal to the holes that they left behind. Hence N should be equal to P, which is what we defined as Ni. We also saw that Ni depends on the temperature because Nc and Nv are temperature dependent. You see this 3/2 dependence, as well as it depends on exponentially on Eg as well as the temperature over here. So Ni does depend on temperature, and as you can clearly see, as we increase the temperature, like for at 77 Kelvin, the intrinsic carrier concentration is 10 to the power minus 20, very small. You cannot get any, you will get ridiculously low amounts of current for this semiconductor. However, at room temperature at 300 Kelvin, we saw the value was still decent, 10 to the power 10 cm minus 3. So we can see that trend, that as we increase the temperature for an intrinsic semiconductor, the carrier concentration increases exponentially rather, because this is a quadratic dependence. This is an exponential dependence, and naturally exponential dependence will win. It's not purely exponential because this term is also there, but it increases exponentially. So a question can come in the competitive exams. For instance, intrinsic carrier concentration, carrier concentration for an intrinsic semiconductor relation with temperature is options: parabolic, hyperbolic, constant, exponential. So now you know, rather than going through all this theory, if you understand the intrinsic carrier concentration, how it comes about, now you can try to solve this problem in your exam. So just not a good problem is not just where you understand one concept. It's when you get an idea of multiple concepts, and this is one such good problem. All right. Okay, so let's quickly move to the second problem now. So now we are required to find the position of Fermi level, intrinsic Fermi level. This means again no doping, intrinsic semiconductor, with respect to mid gap of the band gap at silicon at T equal to 300 Kelvin. So what I mean is that this is your EC. This is all filled over here. This is your EV, and you have holes being filled here, right? This is your Fermi level, let's say EF, Fermi level, yeah, intrinsic Fermi level. With respect to mid gap, what is this entity mid gap? Mid gap is nothing but the average of EC and EV, which I'll denote in this blue color. So for instance, I don't know where it will lie. Let's say it lies over here. I'm calling this as EI. And I'm defining EI as EC plus EV divided by 2, or mid gap energy. EF is your Fermi energy. All right. Now, how do I find this out? How do I find out this entity? Simple. So this is the carrier concentration for electrons in an intrinsic semiconductor, or for that matter anywhere. This depends, just simply depends on EF, right? Similarly for holes, this is the expression. Okay, this is again derived from your density of states times the Fermi function, and you integrate them. Okay, now what I do know is that for an intrinsic semiconductor, n equal to p. We just talked about that. All the electrons that are over here came because they left behind a hole. So n must be equal to p, right? Okay, so let's do that. Let's write this nc exponent of EF minus EC over KT. This should be equal to NV exponent of EV minus EF over KT. What I'll do is now I'll bring all the exponent terms to the left side. So this will give me exponent of 2EF minus EC minus EV over KT equal to NV over NC. Now what I am going to do, I am going to take a natural log on both sides. So this will come out to be 2EF minus EC minus EV over KT equal to ln of NV over NC. Now if you recall the expression of NV and NC, it has a dependence like this. Everything will get cancelled except for this effective mass, because they are at the same temperature. This is pi is a constant, as is Planck's constant. So NC will have Mn star raised to 3 by 2, NV will have MP star raised to 3 by 2. So I'll write it here. MP star raised to 3 by 2, Mn star raised to 3 by 2. All the terms, temperature, Planck's constant, will get cancelled. Okay. Sorry about that. Okay, so finally what I get is, now I rearrange it in this manner: minus EC plus EV, 2EF is there, over KT equal to 3 by 2 will come out, 3 by 2 ln MP star over Mn star, which is 3 by 2. What is the value of MP star? It's given 0.56. 0.56 over Mn star is 1.08. Very good. I'll take 2 below it here, so this will turn out to be EC plus EV divided by 2. KT I'll take to the other side, it will be 3 by 2 KT, and this will turn out to be see what it is, 0.56 divided by 1.08. That's natural log of this, so minus 0.66 into minus 0.66. So and KT, if I'm talking about at room temperature, yeah, it's room temperature, KT is 26 milli electron volts. So that will turn out to be into 0.026 into 3 by 2. So this is coming out to be, this whole entity is coming out to be minus, one second, let me see, making any mistake. Yeah, so I also took 2 common out here. Yeah, so this is coming out to be 25 milli electron volts, the right hand side. So now what I'm going over here, so this will turn out to be EF minus, this entity is nothing but your mid gap, which is also known as EI. This is nothing but your EI. So EF minus EI is coming out to be half of 25 MeV. minus rather. So this is minus 12.5 MeV. Okay, so what I'm getting is that Fermi level minus intrinsic energy level is negative. This means intrinsic energy level is above it, right? EF minus EI is negative. EF minus EI, for in this I have correctly drawn this means. So this means EI is actually above EF by what amount? 12.5 MeV. So 12.5, yeah, this is, I guess, some some calculations I have maybe rounded off it to some different value, but that's fine. More or less this is what I'm getting at, around 12.5 MeV. EF, that's what we find, right? Yeah, Fermi level with respect to mid gap. So Fermi level with respect to mid gap, EF minus EI is 12.5 milli electron volts below the mid gap. So this is that's the mathematics part. Usually what you see is you don't see EI being drawn, especially for intrinsic semiconductor. EI and EF, we typically say they're coinciding. They're not coinciding, and the difference that the reason they don't coincide is the fact that electrons and holes have different effective masses. This is usually electrons and holes will have different effective mass for most of the semiconductors, right? And thus which gives rise to a difference between EI and EF. Okay, please keep that in mind. That is, this distinction is important. One more thing you can see is the temperature dependence. This difference will keep on increasing as the temperature increases. So at T equal to 0 Kelvin, EI will be equal to EF, because remember, effective mass these are constants for a given semiconductor at all temperatures, but it's dependent on temperature. So again, a question can be asked: the difference, the gap between Fermi level and intrinsic energy, or the mid gap, as we increase the temperature, option increases, decreases, remain constants, cannot say. So just from this problem you can understand that dependence, it depends linearly on KT, on temperature. K is a constant. So the difference between EI and EF depends linearly on the temperature. Very good point to catch. Okay, so that was from this problem. We were given an intrinsic semiconductor. We were required to find the difference between the Fermi level and the intrinsic or the mid gap energy level, and we solved the problem. If we saw that arises due to the fact that the holes and electrons have different effective masses, and that also depends linearly on temperature. Okay, so yeah, and this is the NC and NV expressions. I had written that, I forgot to bring them up. Okay, so that's that. Now let's move to the in fact the most interesting property of a semiconductor, the doping. So by doping, essentially, as we had talked in the last session also, is you are adding some impurities. Okay, so add addition of impurities to alter the electronic properties. Here the thing which are interesting the most are the electronic properties. So for instance, stainless steel is an alloy of iron and carbon and among other things, right? Iron, if you notice, iron, if you have recalled, rusts very easily. That brown, for instance, for instance, if you go to some older buildings, especially which are near a body of water, like a beach or any near the river, you see the old the railings made of iron have rusted. They have grown brown. That is because of formation of Fe2O3 and some other oxides of iron. That's rust that has eaten away the iron. Stainless steel is an alloy of iron and carbon, among other things. The thing it changes the material property, that it does not rust. Stainless steel is very high resistant to rust as compared to iron. So there we are changing some properties. The goal of making an alloy there is to change some properties specifically to prevent the rusting. Here, when we are adding impurities to a semiconductor, we want to change the electronic properties. Okay, so here you have a silicon lattice. These are the atoms that you see of silicon. This is a 2D picture. Let's say for some reason in this region A, denoted in red, a red rectangle over here, you have replaced a silicon atom with phosphorus. And you know, if you see the electronic configuration of phosphorus, it has one extra electron as compared to silicon. So that's good in the sense that now it can donate this electron. This electron is free electron now, right? It can move around. So already we have some background Ni, intrinsic concentration, remember, of silicon. On top of that, if we add some impurities, they can donate some extra electrons. That will increase the number of electrons, and thus maybe we can play around with this increased number of electrons to get higher amounts of current. Okay, now there are two kinds of dopings, right? How do we determine that? So let's focus on the silicon semiconductor first, only rather. So in the silicon semiconductor, so if you dope it with entities to the left of it, right? For instance, if you dope it with boron or gallium, you get something called, you'll create excess holes. We call that a p-type semiconductor. These dopants are also known as acceptors. On the other hand, if you dope it with entities in group 5 like nitrogen, phosphorus, arsenic, they donate an extra electron, which it's illustrated over here as an example, right? What they turn is that they turn the now lattice an excess of electrons, hence they are known as n-type semiconductors, and these impurities are called as donors. So these impurities will be known as acceptors for silicon. Remember, my reference is silicon. Group 5 elements, when doped in silicon, when added in silicon, will be known as donors, and the whole system will be known as an n-type semiconductor. And all the semiconductors which have doping in them are known as extrinsic, as compared to intrinsic, which do not have any impurities. We saw nature of doping can be donor and acceptor. Now, how much amount should we dope? So usually, when we talk about alloys, and I talk about stainless steel, there I'm forgetting. I think the carbon is between. I'm forgetting. It's but 1 to 3% or something like that. Okay, maybe even smaller. I'm not so sure about this. But when we talk about semiconductors, right, the amount of doping that we talk about in parts per million or parts per billion. This means, let's say they are 10 to the power 23 atoms of silicon per centimeter cube, but I'm just talking about absolute numbers. So there, what I'll do is that I'll dope it with, let's say, 10 to the power 17 phosphorus. That will be parts per million. If I dope 10 to the power 14 phosphorus, that will be parts per billion. Usually we dope it, rarely you go to higher doping system. There are some applications, true. We'll see in some future sessions that where dope is as high as 10 to the power 20 per centimeter cube. We can dope it high, we do dope it high, but usually it's very smaller, not percentage. 0.001% is parts per thousand means very high doping. Okay, so that's the difference between when we're talking about doping, we're talking about extremely low and extremely controlled amount of impurities. That is very important. Okay, now based on this very simplistic understanding of doping or addition of impurities, let's start to solve some problems. Let's try to get an idea of what amount we are talking about. Okay, so in this it says that a semiconductor is stored with n-type dopant. So when we dope it, this means now it becomes extrinsic. Okay, now it becomes extrinsic, right? And so what we have here is that we have this semiconductor, right? We have this semiconductor and we are doping some n-type. We denote the n-type doping as Nd. D stands for donor. So I write it as 5 into 10 to the power 16 Cm minus 3, and I'm also doping it p-type, denoted by Na or acceptor as 6 into 10 to the power 16 per centimeter cube, and Ni is also given to us. Ni is 10 to the power 16 per centimeter cube, right? We are required to determine, first of all, which is the majority charge carrier. So let's say if there were no doping, right, and then we know that N equal to P equal to Ni, right? This is for intrinsic. Now what you have done is you have doped with 5 to 10 to the power 16 of dopants, this means extra electrons, and also added some acceptors which will accept the electrons. Okay, so but you can see here is that even though background is 10 to the power 16, your Na is 6 into 10 to the power 16 and Nd is 5 into 10 to the power 16. This means we can clearly observe that Na is greater than Nd, and which both of them are greater than Ni. Okay, so what this tells me that this will be a p-type semiconductor or excess holes. This will be the background holes 10 to the power 16, but I have deliberately doped with 6 to the 10 to the power 16 of acceptors and then some donors also, but overall I expect them to be more of acceptors. Okay, now let's see how much extra. So now we have determined that they are electrons, that their holes are in excess. So this is wrong, this is wrong. So only these two options, one of these two is correct. Let's see which one is. Again, law of mass action will stand because that is independent of the for moderate dopings. This will stand fairly easily. So P times N. P is the hole concentration in this extrinsic semiconductor. So P is hole concentration, and N here is electron concentration. P into N equal to Ni square. Okay, so very good. So P into N equal to Ni square. Secondly, there must be charge neutrality, because remember here, when this phosphorus donated an electron, it became positively charged. Charged electrons, we are not taking electrons out of the system. This is just a standalone system, right? This means that whatever holes that are there, plus because donors will donate an electron, they will become positively charged. This is called charge neutrality expression. And this is called mass action, law of mass action. Both of them have to withstand. Let's put some numbers now. What's the value of P? I don't know. That's what I need to determine. So P plus ND plus, this means the amount of donors that we have. What are donors? Okay, this is ND. So I am assuming that all the dopants that I am putting, donors I am putting, they are able to donate electron. Every one of them. We'll see this is not always true, but let's assume that all the dopants that I am putting will give an electron, and thus they become positive charge. So ND plus will be 5 into 10 to the power 16 equal to N. Electron concentration I do not know yet. Na minus, acceptors, they'll accept the electrons naturally, and I'm assuming that all the acceptors that I'm putting over here, each of them is ready to accept an electron. So here this will be 6 into 10 to the power 16. Units is cm minus 3, please remember that. So this will give me P equal to N plus 10 to the power 16, first expression, and then I'll put this over here. So this is P times N equal to, what's the value of Ni? It's 10 to the power 16 whole square. Let's put this value of P over here. So this will be N plus 10 to the power 16 into N equal to 10 to the power 32. Okay, this will be N square plus N into 10 to the power 16 minus 10 to the power 32 equal to 0, right? You solve this out, this comes out to be around 0.6 into 10 to the power 16 cm minus 3. This is the electron concentration, and this whole concentration I can add just by adding 10 to the power 16. So P will come out to be 1.16 into 10 to the power 16 cm minus 3. Okay, what do we notice? Background concentration was 10 to the power 16 centimeter minus 3, intrinsic one. As soon as you add these two dopants, the complexion of this semiconductor block changes. And mind you, I'm not adding that much. This is very small amount, 10 to the power 16. Avogadro is 10 to the power 23 cm minus 3. That's the total number of atoms that this semiconductor block will have. So I'm doping very small, not even parts per million. And still you can see I'm able to change, albeit in a small amount, but I'm able to change the background concentration of electrons and holes. From 10 to the power 16, electrons now reduced to 0.6 into 10 to the power 16, and holes they increase from 1 into 10 to the power 16, the intrinsic one, to 1.6 into 10 to the power 16. Okay, so the option A will be the correct one. But the takeaway from this problem is that first, to identify what is the level of doping that we are doing. The level of doping is fairly close to the intrinsic carrier concentration. Okay, first thing we notice is that, but still even then we can alter the amount of electrons and holes in this problem. And you can see what second thing that you notice, that even the same block, same material, you can dope different types, even the same block. Usually we see P type or N type. Here P type and N type are doped together. This, okay, first thing, what I do is that I try to identify the nature, and that is usually determined just by looking at the values of Na and Nd. So we see Na is greater than Nd, then I was sure that okay, now this must be acceptor type or a p-type semiconductor, and thus holes will be in excess. So this is the first thing that I'll advise you, that this is the first exercise that you should do. Okay. Now, similar problem that we have is this. Now we are given two semiconductors, okay, A and B. The same problem is like before. Like A and B have the same background, so they're both 1.2 eV. Okay, and semiconductor A is doped with 5 into 10 to the power 16 of donors of concentration and 10 to the power 17 of acceptors. Similarly, semiconductor B is stored with slightly higher 10 to the power 17 per centimeter cube of donors, and similarly 10 to the power 17 per centimeter cube of acceptors. But we are required to find what is happening at extremely high temperatures. Okay, what is happening at extremely high temperatures? Here it's given us more than 1273 Kelvin. It's the same problem I have reproduced here. So two semiconductors, A and B. This has Nd1 and Na1. This has Nd2 and Na2. Right? And we are required, otherwise they are the same because the band gap is the same. And we are required to find what happens at extremely high temperatures. So for this, this is taken from a book, Treatment of Energy, very famous book for semiconductor physics. So what you see is that we are seeing here the electronic concentration as a function of temperature. Okay, I like you to recall the problem which we did a few slides earlier, where we see that Ni had this something like square root of Nc Nv and exponential of minus Eg over 2 kT dependence. Remember this, and just look at this dotted line for once. Forget about everything else. So Ni should have a exponential dependence on temperature, because Eg, let's forget about that. Eg is a very weak dependence on temperature. But this expression will we saw that as we increase the temperature, Ni increases exponentially, and Cnv also increase, but they increase polynomially as polynomial function. It increases exponentially, so that's why you see the steep increase, even though your y-axis log scale. See the steep increase, right? What happens and second thing, so this is for just for the intrinsic part. For extrinsic semiconductor at extremely low temperatures, remember that this is how it looks like: EC, EV, and let's say I'm doping, I have some donors here. Okay, this is the donor energy level, ED, which is written over here. Okay, there's still some finite energy difference, so they have the electrons readily available here, but in order to get these electrons from this energy level to here, they need to be provided some energy at where this energy come from. This comes from thermal energy, essentially means temperature. That means at very low temperatures, 4 Kelvin, 5 Kelvin, 10 Kelvin, these, although there are donors there, they cannot contribute their electrons because they're tightly bound to their nucleus, and hence you see very low amount of electrons in the system. However, after you reach sufficiently high temperature, let's say over here at 100 Kelvin, what happens is that because this is very close, this energy gap is usually only, for instance in this problem it's given 0.2 eV, it's very small. So even at 100 kelvins, all of these electrons are donated to the conduction band, and which can contribute now to the, so thus you can see that the concentration of electrons keep on increasing as you increase the temperature up to 100 Kelvin. However, after this, there is no more electrons to be contributed from the dopants, and hence you enter this regime, this flat regime, which is called the extrinsic regime. This keeps on till, let's say, you have at 500 Kelvin or maybe even higher. After that, what starts to happen is that this intrinsic carrier concentration starts on increasing. So here it's primarily due to your dopants. Concentration is primarily due to dopants. All the dopants have ionized, and thus you see a very smooth looking curve like this. After a certain temperature, even the bonds, so even the electrons from here will start coming over there. That's at high temperatures. And that's what you see, you are entering the intrinsic regime of the semiconductor. Okay, these are the three regions. So electron concentration versus temperature. Just to summarize, at very low temperatures, even your donors or acceptors are not ionized, so they will contribute very less to the concentration of electrons or holes. However, at a temperature like 100 Kelvin or something, they can ionize. So all the acceptors can accept the electrons, so all the donors can donate their electrons, and thus the electronic concentration or the hole concentration will remain flat, something like this, which you call the extrinsic regime. If you increase the temperature even further, what's going to happen is that now the background bonds in the semiconductor, for instance silicon bond, will start to break, and now those electrons will leave behind a hole and the electrons will go to the conduction band. This is a huge increase which mathematically is just given over here. How does this extrinsic dependence on temperature look? We'll see in a minute. How it looks, we'll see in a minute. That's how it looks like. But in this problem, we were considered more than 1273 Kelvin. This is not even shown in this plot. So at that such high temperatures, huge amounts of the electronic concentration that is there is primarily, in fact, with the intrinsic semiconductor, which you can see. The intrinsic curve is more or less overlapping with the total concentration. That is happening because this now 10 to the power 15 or whatever the dopant concentration is, maybe 10 to the power 17, like this, is far less than what you have in intrinsic. Intrinsic will go up to 10 to the power 20 or 21, 22 even. Such high concentrations of electrons will come intrinsically. And extrinsic, you have only 10 to the power 17 in this problem. So again, intrinsic will definitely heavily dominate them. Okay, and thus at such high temperatures, the problem was, what is the concentration of electrons and holes? So electrons and concentrate at very high temperatures. Concentration of electrons and holes are not determined by doping, but intrinsic. So thus intrinsically both the semiconductors are same, right? So, and this expression you see over here, NC and NV is everything is the same. So the electronic concentration, which is essentially the algebraic sum of doping plus intrinsic will dominate heavily, and thus the concentration of electrons and holes will be same in semiconductor A and B, because they are the same semiconductor and intrinsically they will behave the same. And at high temperatures, doping does not matter. Only the intrinsic nature matters as far as the concentration of electrons and holes is concerned. Okay, and this we have solved the problem, but this is the diagram. That is a huge amount of questions are usually asked in that, especially in competitive exams. So for instance, we'll see one more problem, but just to illustrate, so they'll say at room temperature, for instance, at room temperature, a silicon semiconductor, a doped silicon semiconductor is more likely to behave as intrinsic semiconductor, extrinsic semiconductor, partially ionized semiconductor. So there are different questions that can be put up from this. Okay, so just try to have this picture in mind. The second thing is the intrinsic concentration, which we saw in a previous problem and again over here. Okay, so now I was saying that it's not always, as we see, that what's called the dopants that you are adding may not always ionize. Okay, so here we are talking about that itself. So when will they not ionize? What happens? We saw at lower temperatures they might not ionize. So let's see. Let's put some numbers to that. Okay. So in this, if the donor level in a semiconductor, so let's draw the semiconductor. We have EC, the conduction band. I'll draw it again. EC, the conduction band. EV, the valence band, and we have the donor level in the semiconductor. So let me draw the donor level first. Is below the Fermi energy level. So let's say the donor level is here, ED, and what they say is the donor level is below the Fermi energy level. So let's say this is my EF, a dotted line, by energy 3 kT. So this energy level has been given to me as 3 kT. Okay, now fraction of ionized donors. So there is actually an expression for this. So we are talking about donors here, right? So we denote usually them by ND. So these are called the atomic donors, let's say. These much atoms I have put. ND plus. Why ND plus? Because they will donate an electron and thus they will become positively charged. These are called ionized donors. Okay, so this is the nomenclature that we follow. So please try to just recall this. Okay, just a second. Okay, so what we are required to find the fraction of ionized donors. So there is a simple expression for that. It is ND plus over ND. That is if the ionized donors divided by total donors is 1 plus 2 times exponent of let me just see I've written this correctly or not. Yeah, this is good. So let's see a different terms. Again, you see this dependence, the Fermi function kind of dependence. It essentially stems from that itself, the because this is follows Fermi Dirac statistics, and thus you see this term again. So EF is a Fermi level, ED is your donor level, which you can see drawn in blue over here. This two comes because of the upspin and downspin. Similarly, I'll write this expression for holes. For acceptors. It is something like this. This is not used in this problem, but you will see in your lecture slides. It will be this term 4 here. 4 because there are two kinds of holes, heavy holes and light holes. So that becomes 2, and plus up and down spin. So heavy up, heavy down, light up, light down. For electrons, it's only up and down. Hence this term 2. Okay. So this again comes from your Fermi Dirac statistics when you calculate those values. So mathematically this factor comes in there. Let's stick to the electrons because we are interested in donors here. So this is the entity that we want to find. Okay. So this will be 1 plus twice exponential EF minus ED is given as 3 kT to me. 3 kT over kT. So kT and kT will cancel. This will 2 times E cube. Okay, you solve this. This E cube I think is around 20. So this will turn out to be 1 over 41. 1 over 40 is around 2.5%. Approximately 2.5%. Yeah, this is an option. This is the answer. So here it's just said that that how many percentage of so even though let's say you added 100 dopants, 100 donors, only 2.5 are able to contribute, rest are useless. Okay, which is clear because so see, another way of seeing is that Fermi level is above the donor level. Okay, so what I have this picture in mind is at 0 Kelvin, so everything below Fermi level should be filled, right? And even at non-zero temperatures, so probability of finding an electron below Fermi level should be more than half. So this means the electrons which are residing here are more likely to be found in ED than over here, because the probability is more than half of being found here. So that's another way of looking at that, saying that so most of the electrons will not even be ionized. So hence the answer should be less than 50%. Can be 30, 20, 2.5. How much low is that you have to determine mathematically, but just a background check that if your donor level is below EF, that's not a good donor. Simple as that, because most of the electrons will be sitting at the donor level itself rather than contributing the conduction band. Okay, same goes if acceptor level is above EF, that's again not a good acceptor. Okay, so yeah, that's that. One second. Okay, so that is about the doping part. So till now, what we have talked about in this session, I have talked about the firstly we talked about the Fermi function, Fermi Dirac Statistics, and when you minimize that that expression to give the number of electrons, the probability of electrons occupying any given energy level. Then we saw density of states, in which we saw that okay, electron can occupy a level, but where are those levels? How are they distributed? We saw that in density of states. Finally, we know the actual electron concentration will depend on the multiplication, right? And then if we integrate it over the whole energy band, then we obtain those expressions for electrons and holes, N and P respectively. And we saw the two cases of intrinsic semiconductor and an extrinsic semiconductor, right? Those are two cases that we saw. And finally we saw that the dependence of temperature, that sometimes, for instance, in this problem on your screen, uh, all the donors or acceptors may not ionize, right? That depends on temperature, which is on the previous problem. And here also depends on the dopant energy level. If it's below EF, it's not a good dopant. Similarly, if acceptor is above EF, it's not a good acceptor. Okay, so those are the things that we need to keep into account while doping. What is the concentration we want to dope with? What should be the dopant, the nature, that is what is the level of ED, and so on and so forth. Now, let's say you have found a good donor or good acceptor.
Means non-degenerate semiconductor in terms of we can say are not compared to degenerate.
No, so all the analysis that we have been doing are based on non-degenerate semiconductors. So what do we mean by non-degenerate? So I'll go to this question that I had put sometime. Yeah, amount of doping. How much amount should I dope?
Okay. So amount of doping here would be considered.
Yes, amount of doping. This I could not find a problem in this case, but it essentially depends on your when EF becomes very close to EC or EV.
Oh,
Because see, EF will shift when you solve your problems, for instance a second assignment, then you will get to know. Okay, EF depends, the Fermi level actually will depend on the doping that you are doing. So we saw that intrinsic level will lie in directly in the middle. But when you dope it, it shifts. For instance, when you dope it with donors, it will shift towards the conduction band. If you dope it with the acceptors, it will shift towards the valence band, the Fermi level. Okay, but there's another catch. You cannot dope it. If you dope it too high, you will see that EF will almost merge with EC. Those, when you dope it such high, we call them degenerate semiconductors.
so
Very high doping will give you something called degenerate semiconductors. We did not talk about them here. Okay, because then the mathematics and all these expressions will not stand in the form that we have written them. Okay, and a good rule of thumb is that if EC minus EF, if it is less than or equal to 3 kT, this means you are non-degenerate now, or vice versa, EF minus EV less than or equal to 3 kT. If either of these two conditions is satisfied, this means you have very high doping and you have a non-degenerate semiconductor. Sorry, degenerate semiconductor. So till now in analysis we have not seen that. If you go through Professor Digvijay's lecture slides, he does talk a bit about it. So I'll recommend, for more details, you go to the lectures. Okay.
sure, sir.
All right. So very good. Now we know we have that much amount of electrons or that much amount of holes. What do we do with that? This information is not particularly useful. Remember, all the devices that we use turn on and off. There should be a current that is flowing through them. This is what we are talking about, is static. All the electrons are there in the conduction band, they're not moving. Now let's make them move. How do you make them move? Very simple. So on your left, what you have in figure A, you have a random motion of an electron in the semiconductor. So you see it's taking this path, going here, going here, going here. It comes down. Its mean position does not change. However, same electron, now electric field is applied to this. Okay, how will it behave? It's still the intrinsic nature. You see the dash, this the one curve is still the same, but you see very slight movement in the forward direction. That is due to the fact that it is now moving in this direction. Net movement is there. Two, again, you compare this curve, this straight line and this straight line. Again, the nature is the same, pointing downwards, but you see, and the slope also, but you see a slight shift again. What happens is that the random motion is still there of an electron, or of a charge carrier in this case. In presence of electric field, it also translates. There is a net movement. This is what is referred to as drift. Drift literally is not literally, drift usually associated in the presence of an electric field. So there is a net movement. In the figure A, there is no net movement. Figure B, there is some net movement. So for instance, you came back here, but here it's not the case. You are here, so you have traversed this much amount, okay, in a given time. So given, let's say, 4 collisions, you have traversed, this electron or this charged particle has traversed this much, and this is what is known as drift. This movement is called drift. And if it's a charged particle, and such an entity is called drift current, because now a charged particle is moving. Okay, so that is dq over dt, over time it's moving, so that's called current, drift current. Okay, here there's a typical example. So this is the semiconductor that you have, and you're applying a bias to this. So this is the let's say an image of an illustration of what is going inside. But how do you do that? How do you apply an electric field? You simply apply a bias to any semiconducting block. Okay, so simply, what is the current? So J is the current density. So current density, I would mean amps per centimeter square per unit area. So that would be Q times Vd. This is the drift velocity that we talk about. This is actually subscript, not like this. Vd is what you call the drift velocity. I was talking about the drift here, right? And this drift depends on the something called the mobilities. As you can see, the drift depends on the electric field. If you apply high electric field, this will move further, right? So that's why Vd is directly proportional to electric field E. This E is electric field. This mu that you see is something called mobility. This is an intrinsic property of any material, like your temperature coefficient or molecular mass, something like that. It's an intrinsic property of any semiconductor. Okay, so if you put this over here, the value of Vd over here, mu E, and the value of mu, by the way, is given by this, which makes sense. Remember, this M effective again comes. This again comes because, remember, I have shown electron moving like this. That's not the true picture. Again, remember the periodic potential like this, the Ronick-Penny model which we had talked in the first class session. So this is the potential, and this is the x, this is the lattice in which electron is moving. We simplify all that into saying, okay, we don't want to do all this. I'll just say the mass of the electron is M effective. So again, this is M effective. This just comes from your Newton's second law. F equal to ma, and you rearrange the terms, you get this. Tau is a average scattering time. You see this time from here to here, the time it takes is tau, the mean scattering time. E is electronic charge. You put all of this over here. So Q, what is Q? Q is Ne. Why Ne? E is electronic charge. N is the total number of electrons, the concentration of electrons. Remember, this N number of electrons per centimeter cube in this. What's the value of Vd? Vd is mu E. So this is your drift current density. This is also known as Ohm's law. We are usually habitual of seeing V equal to IR. This is more or less the same. This is the component I. This is I upon A, right? An electric field is nothing but your V upon D, the distance. So V upon L in this case, right? So I can write this E is nothing but potential divided by L, and this J is nothing but current I divided by the area A. You see this area A over here? This is the same. This is nothing but the Ohm's law, the different form of Ohm's law. Especially in physics, this is where the Ohm's law is stated as this, not the electric counterpart V equal to IR. Okay, so yes, Prem, go ahead. Okay. Okay, so now in this problem we are required to find the mean scattering time of an electron having this much mobility at 300 kelvins. So this is simple. As I told you, the mobility has this expression. So let's just put in the value. So this is 1300 centimeter square. Okay, by the way, the units, so this centimeter square per volt second, again not meter square, because in this we typically because the volume is not high enough, that's why we do this. So E is your 1.6 into 10 to the power minus 19. Tau is something we need to determine. Effective mass has been given as 0.3 times m naught. M naught is your rest mass, which is 9.1 into 10 to the power minus 31. Okay, so what we do is we rearrange these numbers, cross multiply. That will be 1300 into 9.1 into 0.3 divided by 1.6. This is coming out to be 2218 into 10 to the power, 1 second, minus 12. Okay, just a second, let me see if I'm doing anything wrong. 1300 into 9.1 into 0.3 divided by 1.6 is 2218. Yes, yeah, so this is should be 5 7, yeah, 10 to the power 12 seconds. Okay, this should be actually we should also change this, correct. So let me just do that, or rather this should be -4. Yeah, there'll be -4 for when to convert into meter square, because all of this is in SI units, so I have to convert this back. So there will be also 10 to the power -4 term, which will come centimeter square to convert to meter square. So this will turn out to be 0.22 picoseconds. 10 to the power -12 is pico, -4 you come here. So this is the, so essentially this is 0.22 picoseconds. So this is between two successive collisions. Electron is moving like this, like this, like this, like this, and then it comes back. This was the starting position. So naturally there will be different times. So this will be tau 1, tau 2, tau 3, but we will mean scattering time. This means, so for all you observe the time for each scattering, and then finally divide by total number of scatterings. So this is what the mean scattering time, that's what this term mean suggests. This is a ridiculously small amount of time. That's the idea that we want to have. And also it depends on effective mass. So effective mass and mobility, so we see that this scattering mobility is the term we will not refer to as effective mass or tau anymore. The only entity which will have capture this information is just the mobility itself. So tau can be affected by various things. For instance, if you have more, let's say, doping, if you increase the doping, this means there will be more centers which can deflect this electron now. Okay, if you have more charge centers, then tau may decrease. Effective mass is usually is more or less a constant thing for a given semiconductor, right, which we saw that, for instance, in this case it's 0.3 m naught. We see we have seen that it depends on the curvature more or less, right, but scattering time will change, and thus mobility will also change. We usually do not talk about scattering time, we just talk about that, let's say we add doping, more ions and whatnot, the mobility will change. So this is the term which will keep on referring to from now on. It's not the scattering time, not the microscopic thing, but the macroscopic entity mobility. Okay, so how are we doing on time? Okay, we have 17 minutes. I think we should be good. Okay, so in this piece of silicon doped with phosphorus, so let's draw a piece of silicon. It's a piece of silicon which is doped with phosphorus. Phosphorus, if you recall, is a group 5 element, silicon is a group 4, so this will be a donor, sorry. Hence Nd is written. Nd is 10 to the power 18 per centimeter cube. This is a mistake in the units. Okay, 10 to the power 18 per centimeter cube, and this is 200 micron long. Okay, so let's say L equal to 200 micron. Width is W equal to 20 micron, and height, thickness is, let's say, 2 microns. We need to calculate the resistance of this block. Okay, very good. Remember this Ohm's law that we had talked about earlier, right? So I'll simply like this J drift, right? I'll now call it as I upon A. Okay, N E nu. This is the field, which is write as V upon L. Okay, just simply just bringing it to the form in which we are habitual of seeing that. This will be I equal to N E nu times A by L into V, and this will give me V equal to I times L over A times N E nu. V equal to IR, this will be your resistance. So my resistance will be L over A times N E nu. Do we know the values? Yes, we know the values. L is 200 micrometers. Area is W into T. It's 20 microns into 2 microns. Nd, this is the number of electrons. Remember, this is a extrinsic semiconductor, and again I am assuming full ionization. This means each of these dopants, Nd, each of them has converted to Nd plus, okay, 100%. So Nd plus, which will contribute to the electron. The electron concentration will be 10 to the power 18. Electronic charge is 1.6 10 to the power minus 19, and mu is given to us 277. You put in all the numbers, you will get, 1 second to calculate it. So this will be 200 microns. So let me say 2 by 4 by 1.6 by 277. Okay, so it's coming out to be 1.13, and the units will be this is minus 6 10 to the power 6 7 10 to the power 3 ohms. So 1.13 kilo ohms. Okay, fine, we have an option close enough, 1.15. So this block, semiconductor block, has this much of resistance. Now I'll go to the very first thing that we talked about in the first session, tunable conductivity, right? Let's say tunable resistance. How do we do that? So first thing, you can change L and A, but that's say okay, that's not good. I just want to make similar, the geometric dimensions I want to keep the same. I just want to change something which can just give me, for the same length and width and thickness of the same geometrical dimensions of a given block, I just want different resistances. Okay, how do I do that? Simply change the mu or n. Okay, mu, let's say you don't know how to control it, forget about mu, but you can change n. If you change n, you can change the resistance. For instance, if I, let's say, dope it by 10 to the power 19 instead of 18, what will happen? The resistance will now reduce by a factor of 10 instead of 1.5. So let's say 10 to the power 18 per centimeter cube had a resistance of 1.15 K. If I dope it 10 to the power 19, right, it will reduce. It will become 115 ohms, 1/10 of it. Right? So just by changing the doping, that's what we mean. Remember, someone very well put it as tunable conductivity. That's what we mean. The resistance we are changing is by changing this value n. This control we do not have in metals. Metals, if the resistance of a metallic block is 1 ohms, it is 1 ohms. You cannot make it 0.1 ohms with doping it something or stuff like that. Okay. Yeah. So this was that. How many? Okay, we have a few. I have a couple more problems. So in this, consider extrinsic semiconductor with a high breakdown voltage, the saturation field of 30 kilovolts per centimeter. Okay, so let me introduce this concept now. Please remember, okay, we read Vd equal to mu E. So let's draw this. It's a straight line. Vd versus electric field E, denoted in volts per centimeter. Vd is, let's say, centimeters per second. It's a straight line like this, but it does not carry on up to infinity. It's not going like this. In fact, experimentally it's observed something like this. So this entity at which Vd saturates is known as saturation field, which is given here, 30 kilovolts per centimeter. Okay, so now what this question is asking is that now thickness of the semiconductor is 1 microns. Okay, so we are given the saturation field E sat is 30 kilovolts per centimeter. Correspondingly, I can calculate V sat. How? Just multiply E sat by thickness. Thickness is given as 1 micron. So this is 30 kilovolts per centimeter into 1 microns. So you do this, it will come out to be 3 volts. So after 3 volts, so what I am doing is that essentially this is a semiconductor block on which, across which I am applying some voltage V in. V in is varying from 0 to 10. Okay, but we know that after 3 volts the velocity will saturate. Okay, so if I draw it like this, and remember what is the current? Current was Q times velocity. So let's draw current versus voltage. We know Q is a constant, N times E, where N, the value of N is given as 10 to the power 17. That's a constant. E is also constant, times Vd. So till 3 volts, this is 30 kilovolts per centimeter. Till 3 volts, the velocity will keep on increasing because we have not yet reached saturation velocity. So the current also will keep on increasing. However, at 3 volts, Vd will saturate. Vd will, you see, it's flat lines, and thus even if you increase the voltage further, current will saturate. Okay, I'll repeat. Current is nothing but charge times velocity, the drift velocity. Charge is fixed. Charge we cannot increase. 10 to the power 17 multiplied by the electronic charge 1.6 10 to the power minus 19 times Vd. Vd we know will keep on increasing till this corresponds to 3 volts. Till 3 volts, Vd will keep on increasing linearly, and hence the current will also keep on increasing linearly as you increase the field or as you increase the voltage. It's the same thing because field and voltage are related by this expression. However, after the voltage crosses 3 volts, that means your field has reached 30 kilovolts per centimeter. After that, drift velocity will saturate. The drift velocity saturates, drift velocity becomes constant, current will also become constant, and the curve will look something like this. So what do we observe? We observe that current through the semiconductor increases linearly with voltage and saturates beyond 3 volts. This concept, this is known as the output characteristics, or just let's say IV for now. This concept will again invoke when we talk about MOSFET. Just don't worry too much about it. This concept will come again. Okay, now till now I'm talking about the drift current. Second type of current in semiconductor is diffusion current. What is diffusion? When there's a difference in concentration, so you see this concentration is higher, they're more closely packed dopants as compared to this. So if there is a drift, if there's a difference in concentration, so naturally the electrons will flow from this side to this side, right? And thus the corresponding current will be naturally be dependent on the concentration gradient. If you remove this proportional symbol, you will get a constant known as the diffusion constant dn. Similarly, this I'm talking about for holes. Similarly, you can do for the electrons. Sorry, this I was talking about for electrons. Similarly, you can do for holes. The negative sign comes because of the convention that we have assumed that the direction opposite to the movement of the electrons is the positive direction. Hence, this comes. Okay. So just based on this very small understanding, this is the problem. An n-type semiconductor is given. The electron concentration varies linearly from 10 to the power 20 to 10 to the power 15. So here let's say it's 10 to the power 15 centimeter minus cube, while on this end is 10 to the power 25 cm minus 3, and it's n-type, which you see the dopants Nd over here, over a distance of 0.5 centimeters. So let's say this length L is 0.5 centimeters. What is the diffusion current density? Add some, I'll simply just put the nothing to do, just put everything over here. The value of E is 1.6 10 to the power minus 19. This would be 30 into 10 to the power minus 4. Just converting it to SI units. Dou n over dou x, because it varies linearly, I can simply say delta n over delta x. Okay, so 1.6 10 to the power minus 19, 30, delta n will be the difference here. It will be nothing but 10 to the power 20 minus 10 to the power 15 over 0.5 centimeters. Actually, this we did not need that because this is centimeters square. Just a second. Yeah, so it's actually cm minus 2. Okay, so this will turn out to be 1.6 10 to the power minus 19 times 30 times 10 to the power 20 over 0.5. We solve this. Let's do it quickly. 1.6 into 30 into 2. This turns out to be 960 amps per centimeter square. So this will be our correct answer. Nothing happening. It's just that this is just to illustrate. This is just to drive home the point that just by changing the doping from one side to another, there will be a current flowing, because naturally the concentration of electrons, again I am assuming 100% ionization of dopants. That is enough, because see, we are operating at 300 Kelvin, and we saw in that plot, in that concentration versus temperature plot, that above 100 Kelvin, this is a safe assumption, 100% ionization. So here the electrons are 10 to the power 20, here is only 10 to the power 15. So naturally they'll go from this side to this side, and the electrons, charge carriers, are moving over time. There will be a current, which is denoted, which is mathematically we express M in this expression. So to the total current will be Jn, means total electron current due to drift, plus total electron plus current due to electron diffusion. These are the two expressions, Ne mu times E for drift, and this is for the diffusion. Similarly, the total hole current will be hole drifting plus hole diffusion. This expression. What is the total current? Current due to, sorry about this, Jn plus Jp. Simply add these two expressions. Okay, they are related. It's not like that they're completely dependent. So let's say this is the expression. Okay, and let's say at equilibrium, when at equilibrium means I'm not now I'm not applying any bias. So so I leave the system as it is. This is the external electric field that I may have applied, right? And now I'll just, after a certain point of time, I'll leave the system and it will come to its equilibrium. Okay, what will we do? So this term has to go. I'm only talking about the electrons here. Okay, so because I'm interested in finding a semiconductor block which is n-type doped or with donors. Okay, Jn equal to 0. If you do that, you will get Ne mu n times E minus E d tau 1 simply. Okay, now I just need to find this entity and I think I should be fine. What's a concentration n? So n will depend like this. Okay, by the way, the graph looks something like this. Why? Because ef will be closer to ec high when the concentration is higher. So over this ef is very close to ec because the doping concentration is very high over here. Here you can still see a considerable gap, but in both the cases it's below the intrinsic level because it's n-type dope. As I was seeing, someone had asked a doubt. When at the center, at the exact center, let's say at this point, this is neither n-type doped nor p-type doped. It's intrinsic. Hence, this level is EFI. If EF goes above this means you are n-type. The more closer EF is closer to EC, the heavier you are n-type doped. So on this side, on the left side, you see we are very heavily doped. Hence, EF is very close to EC at this junction. Let's see on the right, we are still n-type doped. So that's why EF has to be above intrinsic level, but it's very far away from EC because we are only moderately doped. Okay, hence this is how it will look like, and you do that for every point of time, you get this straight line. Okay, this also depends on doping, by the way. It's not straightforward, but just trust me for this example that we are doped in such a way that EC is a straight line. Okay, so this is the expression for n, right? What I do, I simply differentiate it. NC is a constant, does not change. Okay, this term also exponential, does not change. EC minus EF over KT. EF is a constant, right? CEF is a constant. The only thing is that minus DEC over DX 1 over KT. Differentiate this, you get this. What is DEC over DX? Slope of this line. This is nothing but the potential that I have applied, this electric field. So this turns out to be NC, or rather this whole term is n times electric field E over 1 over KT. Let's put this over here. So NE mu n times E, it's negative sign also, minus E dn. Tau 1 over dou x is this, which is minus n E over KT. Minus minus gets cancelled, your n and electronic charge gets cancelled, electric field also gets cancelled. So what you get is mu n equal to dn over kt. This is your Einstein relation. Mu n equal to dn over kt. The mobility is related to the diffusion constant for any given temperature. Then this is a problem, which is just that. Okay, just a couple more minutes. I think this is the last. Yeah, this is the last problem. So it says that we have okay. This might be then due to from okay, if you do not find similar problems for assignment 2, then we'll leave it, because I was shared this assignment that, and with, so what I am doing right now, the problems that I have is from assignment 2 itself, from some previous year. So I guess they might have gone a bit faster there. Okay, so let's leave it at that. Drift and diffusion not there in assignment 2.
Can I just talk over the mic?
Vijay?
Hello? Yeah, can I just talk over the mic? Is that okay?
Yeah, go ahead.
Yeah, so similar kind of syllabus is there, like the coverage of the syllabus is similar to what we are discussing, but the questions what we find is something different to what we have in the assignment, at least for me, I mean to say.
No, that, so the questions will be different.
Oh, you're teaching just the concepts, okay.
Yes, the idea is there. I tell you, that's why I focus less on the answer. I focus more on the concepts beforehand and the approach of the problem.
Okay, thank you. And one more help. Like I've joined this session very lately,
Okay.
So can you just share me the recording of the session if that's okay?
I'll again just direct the people who are still here. So I have a YouTube channel. This is the link for that. So whatever the sessions that I have posted in the chat box, so whatever we discuss over here, I upload the session directly to the YouTube. So if you miss it for some reason, you want to revisit something, just go ahead and look at this channel.
So thanks for that. Sorry for interrupting you.
No, no, that's okay. Okay, so I'll not push through for this. I've already been pushing a bit too much of diffusion. So I'll revisit diffusion in the next session, and Einstein relation also. But yeah, that's all for this session. Um, Thank you for staying. Thank you for listening. I'll be happy to answer a few questions if you have.